This segment we're going to talk about Dalton's model for ideal gas mixtures. And Dalton's model is just one way that we can relate temperature, pressure, and volume in an ideal gas mixture. And it defines something called partial or component pressures. So say we have a mixture of two gases. So you see that you've got some green dots and blue dots representing those two mixtures. And they are at a given temperature and pressure, where we can define the temperature of each of those components and the volume of each of those components. And Dalton's model defines the temperature and the volume of each component as equal to the temperature and volume of the mixture. Now we say, well, what if we just took one of those components, say the blue molecules, gas A, and we put it in a container by itself? Well, we're going to say that it's at the same temperature as the mixture, the same volume as the mixture, but the pressure is now different. This is the partial pressure. So this would be the pressure that gas would exist if it were by itself at the same temperature and volume of the mixture. Then gas B, we do the same thing. So this is the pressure, partial pressure B is the pressure that it would exert if it were at the same temperature and volume as the mixture. And we see that if we sum it up, if we add the partial pressures, they're equal to the total pressure. And you can see that in the diagram. So the partial pressure of gas A is 1 in whatever units that is. The partial pressure of gas B is 2 in whatever units that is. And then the total pressure is equal to 3. So 1 plus 2 equals 3. So in more generic terms, this is Dalton's model. It says the pressure of the mixture is equal to the sum of the sum of the component pressures, or the sum of the partial pressures, where the temperature and the volume are taken to be the same as the mixture. If I combine that with an ideal gas law, so here I've applied the ideal gas law to the components, and I've written in terms of moles, and you'll see why in just a second. And then I also know, well, if I use Dalton's model, I know that the temperature and the volume of the component are equal to the temperature and the volume of the mixture, so I just drop those two subscripts. And then I apply the ideal gas law to the mixture. All right, now what I'm going to do is I'm going to rearrange things, and I'm going to get an equation where I define the ratio of the partial pressure and the mixture pressure. And you'll see that, well, the volumes are going to cancel out, the temperature is going to cancel out, R bar is going to cancel out, and all I'm going to have left is the ratio of the moles of the components over the mole of the mixture. And I see that this is just equal to the mole fraction. So that's an important relationship, that I can define the partial pressure and the mixture pressure in terms, or I can define the ratio of those two in terms of the mole fraction. So Dalton's model is the one that we're going to use, but there are other models, specifically Amagot's model, which defines, it's the law of additive volumes. So you may see that referenced in other places in literature. It's also very common. But in this class, we use Dalton's model just to keep things nice and simple. So, all right, well, thank you for watching, and let me know if you have any questions.